Yes. We have a super exciting topic today, so has raised a lot of interest amongst people. And it's really nice to be here co-presenting with Harry Kahneman today. This exciting topic of how to apply SAFe to hardware development to you. So we have our webinar coming, and we will get started in a couple more minutes, because there is now 64 persons in the call, and there is something like 140 who have registered. So let's wait for a couple of more minutes so that people can join in. So unfortunately, this recording won't be available public, or that's at least what we discussed earlier. There is some people who are missing this opportunity to see it, and we may share it kind of via kind of specific secure channels with those people who have pre-announced that they can't make it today but are especially interested. Or do you mind, Harry, if we put this out there?
Don't mind. No.
You wouldn't mind?
Of course.
Okay,
no.
Then I guess we could make it public, put it in YouTube. Let's see. We will see. Maybe it needs an editing after that, so we can figure out what to do with the recording. But it's great to see you all here. So now we are 72 people. It's a couple of minutes past. So let's get started. So we are warmly welcome you all to this exciting webinar of how to apply SAFe in the hardware development. We are today here with Harry Kahneman, who is SAFe Fellow and Senior Consultant at Nitor Agile, and who has worked hard on this topic. And my name is Maarit Laanti, and I'm also SAFe Fellow, and I work in Nitor. I have my PhD on scaling agile methods, and I'm working as a Lean Agile head coach at Nitor. So this webinar is free for you, and it's brought to you by Nitor. And if you go to next slide, so Nitor is about sustainable digital development. So we feel that agility and sustainability are close to each other. So we want to make sustainable code, but also sustainable transformations that stick in the organizations and make the workplaces and life of those organizations easier and nicer for everyone, and help this world to go further. So what is Nitor? So if we go to next slide, we will see that last year our net sales were 32 million, and we have roughly 200 digital engineers who are based in Helsinki and Stockholm. We have trained roughly 8,500 people in the agile methods, and Nitor was established 2007. And what we do is we do technological development, we do design, of course, these agile transformations, agile trainings, analytics, and also strategy consultation. And 3 times we've been amongst the top 3 in the best workplace competition in Europe. And that's quite a remarkable achievement, I think. But it's due to kind of the leadership and culture what we have in the organization, and of course the nice clients that we have. If you go to next slide, we can go straight into the topic. So I also see and coach organizations on agile hardware a lot. And the topmost questions that usually comes, which is kind of maybe the primary objection on why not to go in agile hardware, is what about our quality? And usually the organizations, traditional organizations, they have these established quality frameworks and milestones. And this is a thing that usually people say, we can't go agile because we need to X. And the X is something like we need to follow our milestone process. We need to follow the quality practices. People see agile hardware as an oxymoron, something floppy. And I think this is a really nice slide, because what it says here is, and actually I would recommend you to take a look after this webinar on the small video that is embedded here, which is a discussion between Elon Musk and Jim Bridenstine from NASA about what NASA has learned from SpaceX. So it's actually really, really interesting, because they say that, hey, first of all, this what NASA had forgotten was that this iterations actually can lead in the better quality. If you want to achieve something new and radical, you need to do these iterations. And it also helps you to go faster. And of course, then when you actually launch people into the space, then you have to check everything like multiple times, and you have to verify and go crazy about the small details, because cargo you can replace, but the human beings you cannot. And that's the difference. But what they are saying is basically, NASA here is saying that we are approaching a new era where we have a commercial flights to the airspace. And in order to reach that commercial state, we actually have to learn to do things differently. And this is actually true for many industries. So sometimes we hear also this comment that, okay, maybe these companies in US are doing this, but what about globally? What about Europe? Are any companies in Europe doing this? So if you go to the next slide, we will actually see some of the companies who are in Europe actually in the first frontier of taking agile hardware development into use. And if you look like who are the forerunners, we can see that the forerunners in agile hardware, they actually come from aerospace, defense, medical, and automotive industry. And we see this happening, and I'm pretty sure it's going to spread from these forerunners, like agile methods have come from forerunners, almost like commodity. So also agile hardware will spread from these forerunners in the kind of be a way of doing the hardware or the products in the future, because I actually see it that way, that it's not just agile hardware, it's about the product development itself. Because if we see that what has been happening, what is the industry trend, what has been happening in the last years, we will see that by a better and more clever use of software, we are actually going to replace some of the functionality or create some of the functionality that was formerly done by hardware. What Harry is also going to tell you about is these digital twins and simulations that we can use to speed up the development cycles on the hardware development. And that's actually super, super interesting. And that's radical change on how we have approached our product development in the past. So this is a radical change that will lead in significantly lower cost of product development and significantly higher quality and speed, kind of the promises that have always been there with Agile. With these words, I would like to kind of give the stage to Harry. So go on.
Oh, great. Thank you. Thanks. Let's move on to the topic. And you bring up a very good point that video, which I just shared the link in the chat, is a great example of Agile and hardware, and an organization like NASA, as rigid and as safety conscious and quality conscious as an organization like NASA is, that is, if NASA can change, right, then all of us can change. So we want to talk about the topic of agile hardware from the perspective of we have a workshop, right? At Scaled Agile, we have a workshop on hardware development, and we want to talk about some of the points of the key concepts in that workshop here today. Most of the ideas in that workshop are really about changing the engineering's mindset, right? And really the organizations about hardware development. We build highly innovative systems. Those systems are filled with risk and uncertainty. We're not smart enough early to go specify detailed set of requirements and come up with some kind of schedule. So the traditional way of handing a specification to a hardware engineer or even a supplier in the hardware space, and then waiting 8 or 9 months to get a solution back to integrate, right? We have to move away from that and move into something different. And back to that NASA example, those of us who spent some time with NASA, we've seen where we've had to, I worked on a NASA program where the first 9 to 12 months, I believe, or so, we're just about specifying 5 detailed levels of requirements, right? And then later than that, after that, it was a very waterfall type approach. And what SpaceX brought to NASA was the notion of, we're not going to try to fully qualify and build a single rocket launch and make that launch successful. Instead, we're literally going to launch a rocket every 2 to 3 months, right? That's going to be our goal. And each one of those launches is going to gain knowledge and insights in what we have to do for the next launch to gain the next set of information, right? So what we're really trying to do is get back to the kind of roots of engineering we had, where we're trying to explore and learn and build things to gain knowledge that are going to decide what to do next. And somehow engineering became more about management than about innovation and learning. Yet the organizations like SpaceX and Tesla, and really we're going to put some old organizations like General Motors and whatnot, they're doing things now that are trying to move in more of this agile direction, right? And those are the organizations that are frankly doing very well. And that's really what we're going to talk about in this workshop is, what are those folks doing? What's the mindset those folks have, and the practices that they have, and you can apply that at your organization. So let's start off with the first one, which is enable business agility. And this really is the why. We want to start with why. Why can't we continue to build rockets the same way at NASA that we always traditionally have? And it's really the same framing we start with SAFe. Most of you folks that have seen SAFe before, this is how we frame the conversation, that we're in a period of an industrial revolution, a technical revolution in the digital age. And Carlota Perez, who has studied this and looked at the past revolutions, she talks about an installation period where capital pours into some kind of a new technology or new innovation. Back in the Roaring '20s, capital poured into automotive and manufacturing, right? In the age of oil and mass production. At the time in Detroit, I think in the 1910s or 1920s, there were 300 automotive companies just in Detroit alone, right? Massive amount of capital fluctuating in. And then during the turning point, there's a lot of consolidation, and the victors emerge. And at the deployment period, there's only a handful of victors that emerge later. And we've seen that in the .com era, where there's been wildly successful organizations at Facebook and Google and those types of companies. And it's almost as if the victors, we've seen those victors in that era. But they haven't just been software companies; they've also been hardware companies. Apple's the world's largest watchmaker. Tesla designs all of its own hardware for chips and self-driving and autonomous driving. And you think of Google and Amazon more as software companies, but they actually make their own routers and chipsets and network cards. So a lot of these organizations are not just about the software, they're also about taking those software practices into the hardware space, right? They want to be vertical integrators, right? And then it's a great quote from an Amazon Web Service VP up there, who talks about that when we own the horizontal and the vertical, we get to move and change and respond to customer requirements at the pace we're used to, right? We're used to this fast response. And if hardware becomes a bottleneck, like the example in Tesla used to use NVIDIA's, or didn't used to, but back when they first were starting the autonomous driving, they were using NVIDIA's hardware for the autonomous driving platform. And it turned out that NVIDIA wasn't innovating quickly enough, so they had to bring that in-house. Did they know anything about designing autonomous hardware to run AI programs and that type of application? No, but they brought that expertise in house and figured out how to build it, because that was a bottleneck to the performing of the company, right? So the point here is that disruption isn't just about software; it's also about hardware. Now, as we talk to our hardware folks, a lot of people think that Agile's rooted in software. But Agile is really getting most of its influence from product development. And Merit brought that up earlier. It's really about product development. There's the roots of Agile, even the term Scrum. Scrum comes from this article in the Harvard Business Review called The New Product Development Game. In there, this is way back in the 80s, 1986, they were looking at how certain companies, product companies, like Fuji and Canon and Honda, making cameras or copiers, and how they were innovating very quickly. And the insights they got from that were that in product development, they're seeing built-in instability, where leaders set a vision and challenging goals, but give teams the freedom and to implement the best product for their customers, right? They're not giving them detailed plans and specifications. They're giving them just the vision and direction, and you guys figure out your own product plans and requirements by talking to customers and collaborating. Self-organizing teams, that's the beginning of cross-functional and autonomy for teams. Overlapping development phases. We didn't have flow and lean concepts yet, but back in the 80s, but they talked about overlapping development phases, where requirements and design and implementation were all kind of happening together. Multi-learning, that's developing the T skills, as we call them, the cross-functional skills. And then we don't have very siloed engineers, or they're multi-learning and becoming more broad. So the point is that it's not just about the roots aren't in software, even though we like to think they are. They're actually in product development. The organizations such as Amazon and Google that were the innovators 20 years ago, right? They were the innovators back in the software era, circa 2000, right? They created the practices and the technologies that enable them to rapidly deliver software more quickly. And really, that's really the goal of the talk today, is that we're seeing that same capability in hardware where things like Tesla has to say, I'm going to have to develop hardware myself because I'm not seeing that experience going fast enough outside. You have organizations like SpaceX, right? SpaceX wants to launch a rocket every 3 months versus a NASA program will spend years to make sure one launch is perfect. How can SpaceX launch so quickly? Well, they're having to innovate. They're having to do things like down in Texas at the SpaceX Launch Center, they have the world's largest 3D printer because we don't have time to manufacture the next nozzle or the next fuel tank, whatever the next part is. We're just going to manufacture it on site to get ready for that next launch. So they're finding, just as those groups back in the software era invented, Kubernetes and microservices and those types of technologies, we're seeing the same innovation happening over here in hardware today. We'll talk about a few more innovations during the talk today. Last but not least, it's not as if we have to reinvent the wheel here. There is successes, as Mara pointed out. We see organizations applying Agile on hardware. And the last summit we had was in person back in 2019. It's been a while, almost 2 years now. We had a great talk from another one of our SPCTs, Dwayne Bushman, who works in this space. So I encourage you to take a look at that video as well as the one that I shared too about Elon and Jim Bridenstine. All right, let's jump into the topics. The first one is organizing around value for hardware development. We hear this term a lot, organizing around value. What does that mean in engineering? Well, a lot of times engineers work on, I'm a very siloed, narrow skill, and I do layouts, for example, for an organization, and I may do layouts for a bunch of different products. In an Agile, we don't work on multiple projects, multiple products at the same time. We're 100% committed to a team and getting the team's work done. So that's a change. That's a change in mindset. So in Agile, every individual is a member of a team. That team is part of a larger team of teams. It's in what we call a development value stream, developing a product or solution for their customer. And safely call that an Agile release train. And those Agile release trains are realizations of those development value streams at the portfolio level that are trying to realize a strategy for a portfolio or for an entire business. But the message is that, those individuals are on a team. So in the workshop, we take a look at, we have an example that we use, and it's autonomous driving, it's an autonomous vehicle. And we focus on this camera team, and we talk about the fact that we use this example of a camera team to say, if we're developing a new camera, some kind of innovative camera that's low light or far distance, maybe new image sensor technologies coming out, what type of skills will we need to have to build that camera? Well, the camera is going to have an image sensor, and it's going to probably have to convert that sensor signal, probably an analog signal, into some kind of digital format like HDMI. So we may need an FPGA and some kind of analog to digital conversion technology. Those two parts have to be integrated together, probably on some kind of custom printed circuit board, eventually housed in some kind of mechanical enclosure to be mounted on a vehicle body, and then a connector off to the vehicle control that's going to be taking that signal and doing something really cool with it. Those are the types of skills that needed, but we expand that to say, well, I need to know how to mount that camera on the vehicle body, so I may need to be collaborating with other people. I didn't know how vehicle control is going to use that signal. So there's a bunch of knowledge that needs to be happening that the camera team needs to get their work done. So the challenge we see in hardware is that most engineers, as we mentioned, have worked in silos and only performed really their functional work. When it comes to working on an Agile team, how the work on the team is not usually balanced this way, right? It's not always balanced that there's equal amount of mechanical work and software work and electrical work. So a lot of times, if you've ever worked on an Agile team, we see that we have to help other team members out, or swarm, or collaborate on work. And for example, and I've seen this actually in hardware teams, where a software engineer may have to help a mechanical engineer out and get some of their work done. We don't expect that software engineer to do any of the detailed mechanical, designs and whatnot that they're not trained to do, but they might take some of the burden off, and they may launch Pro-E, for example, and rerun some regressions, or whatever the work needs to get done, the stuff that's just kind of the day-to-day redundant type work, to let the mechanical engineer for that iteration anyway, or that day, get the more detailed work done. So really the challenge for Agile teams is they operate best when they can collaborate on work like this, yet especially in hardware engineering, we have those very vertical silos. And really the goal then is challenging those hardware teams, at least initially. It's a challenge initially, because they have those deep, broad skills. But the organization, the message our hardware engineers too is the organization needs both. Certainly you work on this collaborative team and you're going to gain those cross-functional skills, the multi-learning, as we just called it in that new product development game article. We still need that deep domain expertise. However, to do faster flow and faster work, we need those cross-functional skills as well. And certainly those skills can evolve over time, or the need for those skills can evolve over time. We show here 3 examples of how teams might be formed to get work done. The first one is a highly innovative environment with frequent experimentation and tight collaboration where we're iterating quickly. Maybe there's that new image sensor's out, so we need to be prototyping the image sensor with what kind of signals it's going to generate and experiment with different light conditions. At that point, we need mechanical, electrical, and software collaborating together on a daily basis. We're going to daily stand-ups together to find out what limitations there are and how can we help each other get something done. As the innovation, we mitigate the risk and mitigate certain uncertainties with that design, well, now we're just really designing the part. So the mechanical electrical engineers, they can start focusing on their aspect of development, right? I'm developing my mechanical electrical aspects and I'm developing my software aspects. We don't collaborate daily, we might integrate, every iteration or so, or every 2 or 3 weeks, or 4 weeks. But the need for that daily collaboration isn't the same. So we're on different teams, maybe on the same development diagram, same agile release train. Probably not an example for the camera, but certainly there's another model where there's a platform. The hardware is more of a platform, so that electrical, it's a separate development value stream that has a roadmap and certain milestones, and the software is just integrating on it as a platform. And certainly this can evolve over time. As there's more unknown and uncertainty, we need the tighter collaboration. As there's less unknown and uncertainty, we're just developing the product for production use. Then we move to those other types of models as we see. But all 3 of those examples are certainly valid ways of collaborating. Next, let's jump to embrace variability and preserve options. Delaying decisions is not a typical characteristic we see in engineers. Engineers like to decide, right? Deciding we assume is mitigating risk. However, we need decisions that are based on objective evidence of knowledge that's gained through learning, right? Otherwise, we are building up this large batch of decisions, the unvalidated decisions that cause us surprises downstream and surprises later. And I think there's no better example of this than the Wright brothers and Langley, as contrasting their approaches in the race for flight. Langley was well funded. He had a specific design that he spent a lot of time specifying requirements, doing design, very traditional waterfall approach at the time. Where we contrast, and of course he was never successful. It was the Wright brothers who were successful. And they broke down flight really into 3 fundamental parts. We don't know how we're going to create lift, so let's determine how we're going to create lift. Then once we have lift, how are we going to control the vehicle, control the plane? And then once we can control the plane, the machine as they called it, how can we generate propulsion to move it through the air? So they really broke it down into solving these problems. And then they started a set of experiments. We have to start with the first one, lift. How are we going to get lift? Well, we modeled things on paper, and then we invented, right? Just as SpaceX has the largest 3D printer, the Wright metal printer, the Wright brothers had to invent the wind tunnel, right? We're going to model different wind shapes and create this wind tunnel that's going to actually do some measurements of those wind shapes. Once we have a wind shape, a wing shape we like, let's build a kite and see how much lift we get out of that kite, and eventually a glider. So they did a lot of experimentation and building mock-ups and simulations and even building the infrastructure like a wind tunnel to make that happen. And that's really what we're not asking hardware engineers to produce a new version of their part every 2 weeks. Instead, in small batches and iterations, instead we're asking them is to gain new knowledge through simulations and models and other experiments, right? That validate that we are going to be able to determine the lift by a certain period of time or in time for the product. And really the point of this is that we know we can't reduce uncertainty by providing more detailed specifications and project plans. That's the notion of flexible specifications up there. We have to do something that creates knowledge, right? And getting more detailed plans or creating more detailed specifications doesn't mitigate risk and reduce uncertainty. We need to do something. And that's really what the Wright brothers did in contrast with Langley. And certainly we can create plans from a set of demonstrable milestones, right? And once we have those milestones along the way, that's really what SpaceX has done with their launch. We have a new launch every 1 to 3 months, right? And each one of those launches is a planned experiment that's going to gain some new knowledge that's going to feed back into the next launch and the next launch, to eventually fulfilling the mission of whatever SpaceX is, to take the big heavy rocket to Mars or whatever. I really don't track that as much. But contrast that to the old way of NASA, where we have, hey, the requirements are complete, the design's complete, right? It's a cultural difference between how NASA and SpaceX approaches a problem. NASA wants to launch one time and make that launch perfect, and they strive to create perfect requirement specifications and fully qualify every part. In contrast, SpaceX just says, let's launch the next rocket because we need to experiment faster. And really, this is fundamentally this is really just safe principle 5. We want to base milestones on objective evaluation of working systems. And as Alan Ward tells us, development and engineering and innovation, really all of those are more dependent on what needs to be learned rather than what tasks need to be to move through a gate. So we want to move away from those more traditional milestones, traditional gates that we have, and more towards ones that are demonstrable. And we need good leadership, because not all those learnings are going to appear successful, right? So Elon, who is the business leader as well as the chief engineer of SpaceX, tweets out after a rocket crashes on landing that, hey, we got all the data we needed, because he knows, and leadership knows, that it's about learning. It's not about ensuring that it looks successful. And we don't mind that rocket crashed, because guess what? We have the ability to we're already manufacturing the next rocket with the new innovations and the new designs and the new et cetera that we're going to be launching in 3 months from now. And not all learning is that expensive, right? Certainly it's the case that each launch is launching multiple rockets appears. In fact, I should back up to that slide. It might be the assumption that launching multiple rockets is much more expensive than launching one time. And that can appear to be true. However, SpaceX has done things, and that's what we advocate, to learn more quickly. How can we build the rocket faster? Well, we have the largest metal 3D printer, for example. And there's certainly other aspects that SpaceX has that try to drive down that cost. And if you look at that video that we just shared of Jim Bridenstine at NASA, he's talked about the economic benefit of the relationship with SpaceX, how they've gotten many more launches off than they thought they were going to get when the relationship started over 10 years ago. So the economic value has been even better than they thought. They've gotten more launches and more launches from SpaceX than they thought they were going to. So it's also true that the economics are there for this approach too. And it doesn't seem intuitive, but if we factor in what Don Reinerson tells us is the cost of delay, what is the cost of delayed learning as opposed to being able to launch more quickly? If NASA could launch their rocket 2 years early by doing these little mini launches, how much more value would that have to an entire program? We can take that 2 years worth of money and shift that into launching more soon, building rockets quicker, building rockets in smaller batches. There's other ways of learning as well, though, and I think Merritt pointed this out. Merritt pointed this out with digital engineering, right? So we see a lot of organizations trying to shift learning left by doing design and verification in smaller batches with digital tools. I don't think that the infrastructure there, this is one of those examples where we see the hard organizations that are becoming more agile, starting to integrate models or do simulations and investing a lot more in the digital world. The tools that I mentioned are still catching up, the Mentor Graphics and those types of companies. But there are tools like Model Center that are starting to take integrations of these tools and be able to do simulations across multiple different tools. One of the examples of a success story here is General Motors, right? We have a legacy mainstream company, large, and they adopted digital engineering practices, at least on the Hummer EV. There's articles out there from the end of last year where they talk about how the CEO challenged the engineering team to get the Hummer EV done in 2 years, where they traditionally take 4 to develop a new platform. And they went back and said, hey, they pushed back and said, we don't develop platforms that quickly. And she said, well, you have 2 years. The market's not going to wait 4, so let's do it in 2. And they were successful. They met that deadline. And they did so, and as the articles talk about, by doing a lot more learning and testing in the digital space, and a lot less of it in the physical space. So there's an example of early adoption. People are innovating and finding ways to shift that learning left. Now, if we're going to build and demonstrate more frequently, then we've got to invest in that infrastructure and that technology. We saw some examples of that. SpaceX has the largest 3D printer in the world. GM has shifted a lot of their work into a digital environment, which not only was a success for them with the Hummer EV, but it was very fortuitous because COVID hit. So since we were doing more work in the digital space, that was a good thing since we had to spend a bunch of time at home. So these software organizations, they've spent a lot of time inventing the technologies that are going to decouple their systems and enable frequent integration. That's where they've seen success, right? We want to integrate more frequently. The faster I can take changes, the faster we can take small changes, integrate them into a larger context, the faster we can learn. So certainly it is sort of the case that hardware domains experiment, right? We know in our domains that we're not that smart. So we use models and simulations and breadboards and foam mockups and other prototypes to do learning. And the goal then is to pull that learning left and get those changes in as richer context as quickly as possible and as economically as possible, right? We still can't forget about the cost of building things. The challenge is that a lot of that learning is done in a local context. If we were in a more traditional approach with our camera, we might have the mechanical engineer that's designing the enclosure. They have their spec and they're modeling their designs and their 3D parts, and they do models at first and 3D print them and maybe play around with the chassis group and see how the camera is going to fit on the body or on the chassis, and eventually move to manufactured parts. And if I'm designing the printed circuit board, well, I'll be doing, again, more modeling, and I might do a Rev 1 of hardware and go spin those boards, and then maybe have a Rev 2 when there's a new image sensor out. And if I'm the FPGA designer, for example, I might be using the vendor simulation. I'm software in the loop initially, and maybe using their hardware kit for some hardware loop. And eventually I'll get that first Rev of the PCB board. So now I can actually do my FPGA on the board with the peripherals and start designing more logic that way. But traditionally, these folks are working in isolation. The reason we want to put them on a team is we want them to accelerate those innovations. Yes, we have a camera schedule. We want that camera to be done more quickly. How can we take the enclosure and the PCB and the learnings of small changes and integrate them more quickly? And there's a great book out. It's a couple decades old by Nitor Agile. And it's called Lean Machine. And he's an exec from Harley-Davidson, talks about how Harley did their lean transformation. And they made these integration milestone points where all the hardware, and Harley back in the day, especially way back up 20 years ago, it was all mechanical, right? There was probably very little software in those motorcycles back then. So they used integration points as regular cadence to integrate the entire motorcycle platforms and see what they would have, right? So there's this notion of adding a cadence with a vision, a challenging vision and direction for the team is really the motivating factor that gets the whole system learning and not just individual silos functional skills. And the notion is, again, we don't want to let those individual changes sit idle. We want to take those changes and integrate them as richer context as we can, as quickly as we can. And this isn't an uncommon practice. Most organizations have what I've heard of Franken missiles. I worked on a missile program before. They called them Franken missiles. And basically it was taking legacy parts from other parts of the organization and getting started with something, right? And really we just want to take what kind of is happening in engineering and make that the regular schedule, right? So instead of having this fictitious schedule up here with those phase gate milestones, where the engineers down here are kind of taking all kind of legacy parts and trying to integrate them and trying to learn quickly, let's just call that the regular schedule. Show me X at this milestone, show me Y at another milestone, show me Z at another milestone, right? And what enables that is putting everyone on a common cadence. And the notion at scale is we don't just even want one team learning that way. We want the entire program learning, right? So all the vehicle programs spread across all different kind of parts of the system. So they're all on a common cadence. In fact, we see this in automotive. Automotive is on a 6-week cadence where they're continually integrating. I've worked on multiple automotive programs on the supplier side and one time with the OEMs. And most of them are on a 6-week cadence. We're constantly, I was on an infotainment program where every 6 weeks we were giving software and firmware of the latest changes, and then occasionally the hardware, right? We don't expect, again, new hardware parts every 6 months, or every 6 weeks. But we certainly expect those software changes, and the hardware changes will happen whenever they happen, whenever we do a new board spin or a new rev of the mechanical parts. All right, to make these frequent changes happen, we have to design these systems for change. So certainly we see that modular designs is kind of an old statement. I'll just say that it's an old statement, and hopefully it's not anything new, but we have modular designs that have well-defined interfaces, and those support efficient changes. It's something we've been doing in engineering for quite some time. We use modular design to create scalable, reusable modules and decouple parts of our system. But what we need to do is to make the point that the modules have that intentional interface, not just for software, but also for electrical and mechanical connections. My background, I'm rooted in software. So I've been talking about, standard interfaces for quite some time, APIs and those types of things. But it's certainly true that interfaces also exist in the hardware space. We have the physical connection of our camera. How's it going to be physically mounted to the vehicle body, as well as electrical connections. How's the camera going to electrically communicate with vehicle control? And we looked at some of those examples. Each one of those has specifications, right? Some of those are industry standard specifications like HDMI, where the physical mount might be weight and heat and material transfer and whatever kind of physical properties there are when we connect two parts, right? The camera to the vehicle body. Now, what interfaces allow us to do is to iterate over our designs. So as the camera team is evolving their design, so long as they don't change the interface, as long as we don't change the interface from our camera team, vehicle control, for example, could begin using the dev kit. So we're getting some initial logic about how we're going to do the A to D conversion, and we're doing that in a dev kit, and that's what the vehicle control uses as their interface does. As we move to the first rev of hardware, maybe the second rev of hardware, and eventually the production camera, we can give something early to vehicle control. So vehicle control doesn't have to wait for our final production camera to start integrating with us. They start integrating when we have a dev kit. We've got wires on a breadboard, and then the first rev of hardware and the second rev of hardware. And it's really that mindset that we talked about in the last section, to get the whole platform integrating and to get that kind of Frankenstein, the Franken system being built, right? And it looks funny at first. It's not obvious the production format or form factors, but certainly we can have the image sensor integrated with a breadboard with some kind of FPGA, and we can actually give an assembly of that to vehicle control for them to integrate with. So we're trying to shift the learning left and shift that integration left. And this is how we're going to realize those cadence-based learning cycles across entire platforms. And this is really nothing new. The main thing that's really new, this is what we've done in the past, but we're actually calling this out in the schedule, right? That's probably one of the main differences, that we're admitting that this is how we develop. We develop through learning and doing instead of trying to meet phase gate milestones. And it's not just true in electrical, it's also true with the mechanical aspects as well, right? We can 3D print things. We can integrate CAD models. That was the example we saw back forward with General Motors. We might take our two CAD models and integrate those to understand, are the holes lined up, the screw holes lined up properly, or is the heat transfer going to appear properly? Those types of things. Once we have those interfaces, we have to consider how the electrical and mechanical design decisions impact change. And we're focused on electrical first. And really, it's important to think of it that this applies not just the operational environment, but also the development environment. How quickly can we make changes in the development environment while we're developing the system? I have a good colleague. In fact, I was just thinking, preparing for this presentation, that I haven't seen him in about 2 or 3 years now. So I'm not sure what the number is, because we haven't had face-to-face conferences anymore. But he works at Mentor Graphics, and he was telling me that we're talking about Agile and the approach to Agile and the use of programmable devices over custom one-off ASIC, application-specific IC integrated circuits. ASICs, as you probably already know, once we program logic into them, it's fixed, right? They're manufactured with the logic embedded in them. Where FPGAs and system on chips, they're programmable. And he was telling me that the number of ASICs designs is dramatically decreasing over the last 5 to 6 years, and this was 3 years ago, so maybe eight years or so. And as more people do designs that are based on FPGAs, not the number of parts produced, by the way. He didn't say number of parts, but the number of unique designs. So we do see an industry trend away from ASICs and more towards programmable devices. And what that and the reason I think that is organization becoming more agile. I can't live with these fixed hardware and to go back to manufacturing to make changes. I've got to find ways to more quickly make that change, and the solution has been reprogrammable devices. So while ASICs are cheaper, they have lower unit costs, they consume less power, the industry is moving more towards programmable devices. Again, it's that cost of delay. I'm going to pay more money to put parts in, and they're going to consume more electrical power and maybe manufacturing costs, unit costs. But the value I gain is the ability to make change, to reprogram them. So we see more organizations favoring those programmable devices. Also, we have to be more intentional about the permanence, right? Pretty famously, Tesla, even though they moved off of the NVIDIA board onto their own hardware, they were still selling cars with the NVIDIA board, right? So the Model S 4 or 5 years ago, when they released it, had the old what they call the hardware 2, and they knew they were working on a hardware 3. Yet Tesla was able to monetize and sell the vehicle, and owners were able to purchase the car knowing that I'm going to be able to upgrade to that latest hardware when the time comes. And certainly, so Tesla had designed that hardware to be non-permanent, right? Some had some kind of electrical connector, and it was mounted someplace that could be easily removed. So they had designed the vehicle in to be able to make those changes. They weren't user replaceable, but you could send. I think Tesla doesn't even have dealerships. Instead, they send folks out in trucks to go make the changes at people's houses. So they had designed that in the cost. The same is true with mechanical, right? And that's really the mechanical example that I just gave is how are we going to mount this board onto this device onto the chassis or the vehicle body. Is it a permanent through weld? Welds are cheaper. Is it a permanent joint or a non-permanent joint? We can screw it on or use other kind of fasteners. But we also have to understand, is it going to transfer the material properties? There's probably a lot of heat generated by that. How do we dissipate that heat? Does it have to get off to the body? There might be fluid properties, light properties, force properties. How much does it weigh on the body, et cetera? So we have to make sure that however we decide to join those two parts, that it meets all the material properties. But again, the move is away from physically connecting things and making them more kind of software controlled. And really, that's kind of how I want to end it is kind of, and this is really a slide right out of the workshop, is getting hardware engineers to think, what is the value? Granted, there's added design costs with doing these things, but what is the value it provides the business and or end user? For example, all the software in Tesla, the autonomous driving, the settings, apps, et cetera, they can be updated over the air. What's the user benefit? I think we already talked about that. The user benefit is I buy the car and I can get the same value over time, right? I bought the car 4 years ago, but I have all the capabilities that a new car would have. Huge user value. What's the business value? Well, users don't delay in purchasing, right? I can purchase today knowing that I'm going to have that value later on and over time. So your car now is almost like your phone, right? I don't buy a phone every new year when they come out. I don't need to because the software updates itself and most of the values in the software. The second bullet there is what's the autonomous driving is the autonomous driving hardware, as we mentioned, was designed to be field upgradable. Started out with the NVIDIA board device, and then they moved to theirs 4 years later. Again, there was no cost of delay as a Tesla owner. I can buy the car today and know that I'm going to be able to get those updates. Oops, excuse me. Oh, shoot. Sorry about that. A little hiccup. And last but not least, and this surprises me, is that almost every mechanical linkage in a Tesla vehicle is software controllable. Sorry, I got to refocus my screen here to get closer to you guys. The door handles, the door locks, the glove box, the trunk, the front, even the HVAC vents. This shocked me. A friend of mine, I was in her Model Y the other day, and adjusting the vents for, usually you have a little mechanical dial to move vents around, right, to move it up and down or left and right. In Tesla, they're in the app, they're in the screen. You actually go to the touch screen and you adjust the vents that way. Even the vents, the ventilation system is also software controllable. So what are the benefits to that? What are the costs, right? There's probably nominal costs for a little actuator to sit in there to adjust the vents, and we had to design the software interface for it. But there's been examples of Teslas getting benefits from having all these linkages that are software controllable. They were able to do, there was an example where a crash occurred and nobody could open the glove box, right? Because it had been smashed and they couldn't get to their paperwork. Well, so Tesla, of course, with an over-the-air update, designed the vehicle to say, hey, if you detect a crash, open the glove box in case it gets blocked from being opened because of the collision. There was also some examples where Tesla did an over-the-air update Consumer Reports had downgraded them because of a setting. So they downgraded them from a recommendation to a not recommended, because by default, the autonomous driving didn't automatically take over the vehicle. You had to go in and change the setting. Well, Tesla made a change literally the next day. So, how is that to respond to business agility, right? The business says, hey, Consumer Reports has downgraded us from a buy or from a recommendation. We can fix that literally the next day because we have this continuous delivery pipeline and that ability to make changes, send those changes out to the field. All right, so we've got about 15 minutes or so left for that. That's all I wanted to talk about. Again, this is from our Scaled Agile's How to Do Hardware with Safe. We have a workshop that is available to our consultants and our enterprises. So we just walk through a few examples of what that workshop looks like, and getting hardware engineers, and also not just the engineers, but also the leaders, the hardware leadership and engineering leadership, to start thinking more agilely about how we design our hardware-centric systems, and then also the economic benefits of it, right? There is economic benefits. We're seeing you're not alone, right? People are starting to do this already, and they're seeing the benefits from it. So with that, let's go and take some questions. Do we have any questions?
Yes, we actually have some questions in the chat, and please post some other questions in the chat. So there is a question: was the workshop already available for SPCs?
Yes, it is. You can reach out to me. It's available to SPCs for our partners and enterprise customers. So feel free to reach out to me at harry@scaledagile.com, and I can get you connected with it. You should see it available in the toolkits for those folks.
Then there is another question. How can we learn more on the risk mitigation best practices for agile hardware development?
That's a great point. Really, how we frame this for most hardware engineers is risk mitigation, right? For software, we can call it, hey, I'm doing spikes, or I'm learning. A lot of that learning in hardware, we call it risk mitigation activities. In a traditional waterfall environment, we're just talking about building the product. We don't talk about learning and gaining new knowledge. But yet that's really what we need to do. As we talked about before, there's uncertainty, there's risks, there's variability in the products we're designing. There's things that we don't know and we don't understand. And the only way to gain certainty, as we mentioned before, is to actually do something, build an experiment, a wind tunnel, build a kite, a glider, as we saw the Wright brothers do. Those are the risk mitigation activities. So I'm not quite sure what was the question again? How do I learn more about risk mitigation best practices? So really, the risk mitigation best practices are doing those experiments, right? The example we used was the Wright brothers. They had to mitigate risk of dying on a flight, right? How am I going to fly on this plane and not die? You see those old examples of people taking their flying machines, flapping and going off a cliff and hoping that it works, right? Well, the Wright brothers were much better engineers than that, right? They wanted to prove things along the way, right? That was the goal.
It's actually really interesting in this Harley-Davidson Lean story. There is a graph that says, hey, have you ever thought that actually you learn most when 50% of your tests fail? So this is actually against the traditional thinking, because usually we think that, okay, the quality tests are something that our hardware should actually pass it always. And if you always pass, then actually there is no learning. So when you actually do iterative learning, that means that ideally 50% of your test fail. And that reminds me about Elon Musk and one of the SpaceX rockets, when it was actually blowing apart in the air, and he sent this tweet to his people that, hey, what a great learning, that we learned so much. Yeah, exactly this slide. We got all the data that we needed.
Excellent example, and you bring up a good point. I think I saw another one. Training available for hardware leaders. We recommend that you take not just your hardware engineers, but also hardware and engineering leadership through this workshop for exactly that reason that you point out. They have to buy into the fact that we're not just building the product, that we are doing these kinds of experiments. Because as an engineer, I'm going to be evaluated by my leadership and make sure that I'm doing things the right way. So we need them on board with this approach as well.
Mm. There is also a comment that ASIC designs are rising nowadays, which is a big trend, and that organizations need more performance with lower cost and lower power consumption. And there is a limit reached with software and general purpose CPU designs. I think it's always a balance between cost and flexibility. In general, if you allow flexibility in the hardware, like allowing a little bit wider interfaces so that you can have decoupling and interchangeable parts, interchangeable design and extendable design, then actually that usually has a bit higher cost. What do you say about this, Harry?
Yeah, it's important. I had heard the opposite. I worked. I had a good colleague that I would see at the NCOSI conference every year, and he was an exec at Mentor Graphics, and he was one that actually, excuse me, he was one that actually told me that they're seeing, it was I think a 5 times, and this is not the number of parts. This is the unique designs, right? So certainly those high volume parts, like in my cell phone or something, there's probably certainly many ASIC parts in here for doing, you know, little properties to it. But when I have to do an over-the-air update, when my Android phone is going to update itself, obviously that update has to go in something that is programmable. If I'm going to, you know, change the firmware, change the software, certainly the apps are obviously in some kind of, you know, flash memory, but the actual loading and those types of things that are in the programmable devices. So I've not heard that. That's not what I had heard, that there'd been a move towards those. There's been a move for the unique designs. There's more designs being done with the programmable devices. Although there probably certainly is still a lot more manufacturing of those ASIC parts. The number of ASIC parts isn't going down, but the number of unique designs and FPGAs and system on chips was going up.
Yeah. So I think there is also, what you are saying is basically that there is this design exploration in a way that is done with the programmable logics. And then there is kind of what we manufacture is slightly different, because then we actually have already figured out what we are going to deliver and maybe mass produce that. Is that what you are saying?
Well, there's still a lot of ASIC parts, right? The number of ASIC parts isn't necessarily, ASICs aren't going away. I didn't want to give that message, right? Certainly they still have their purpose, and especially those very high volume parts, right? If we have a lot of programmable, a lot of parts in here, you know, for power consumption and space and whatnot, there'll probably be a lot of ASIC parts in here. But and you bring up a good point too, is that not every area of our system is going to be innovative and have to evolve, right? We pick the areas where we know we're going to evolve, and we design those in. Another great call that I should have made here, and we do it in the workshop, is to WikiSpeed, right? And the WikiSpeed, if you go Google WikiSpeed and Joe Justice, he talks about designing modular designs, right? He doesn't actually, on his chassis, where he has a car, he's got this car that he's done rapid prototyping with, and when he mounts the struts to the vehicle, he uses an adapter, right? He uses kind of software patterns that we've known. Now, so the struts don't mount directly to the car. That way, he can kind of use any struts and any vehicle and any chassis, and then the adapter, he uses an adapter to decide where to mount that thing. That would obviously add material costs. It would add manufacturing costs. It would add costs, but there's a benefit to that design at that point in construction. Now, you don't add material costs and put adapters everywhere in the vehicle. You just do it in those points that we anticipate there to be change.
Yeah.
Excellent
good
point.
Points. Yeah, excellent points, and good areas is to look where the technology is more rapidly developing and bringing actually benefits, or where the company wants to be kind of top notch. Those are the areas to explore. There's a question about what are your favorite videos or recommended videos on this hardware design, or any books that you would recommend.
Yeah, certainly. We talked about 2 of them. Alan, for hardware engineers, that Nitor Agile Lean Machine book is always a good read. It's a nice, easy read. It's about a story. It's a story about Harley Davidson, so it's kind of fun to read. It's on motorcycles, really well written and a good story. Alan Ward also on lean product development. He's as another great book that talks about hardware. We get our set-based design and a lot of we got our development and operational value streams and say from that book. So a lot of good insights there. If you go to the Scaled Agile frameworks, scaleagileframework.com. And in the lower left corner, there's a link to advanced topic articles. One of those articles is on applying SAFe for hardware development. And we have several links to the videos we talked about here and other books as well. I think there's 7 or 8 links to additional reading and additional videos there.
My favorite book is Preston Smith's Flexible Product Development, which is explaining some of the basic concepts out there. And it's a bit old book though. And then one of the favorite videos is Robin Yeaman from Lockheed Martin made a nice talk on SAFe Summit. Was it a year ago or 2 years ago? Do you remember, Harry?
No, I haven't heard that book before. What's the name of the book?
Not Preston Smith's book on flexible product development. Sure, but then Robin Yeaman's talk on SAFe Summit about Lockheed Martin.
Yes, so if Vimeo, that video would be on Vimeo's site, but I don't remember what she was referencing. You're talking about what she was referencing in her talk?
Oh, okay. I think that was nice. And she's also talked in Agile Hardware Conference, which is she talked about cross-functional teams in hardware design. And it's a really nice video as that one as well.
Yeah, and she Suzette Johnson at Northrop Grumman, Robbins from Lockheed Martin. We're in Gene Kim has a group that puts out papers, articles. And if you go to Google industrial DevOps, so a lot of Robin and her collaboration with Suzette, it's been branded industrial DevOps. And if you go to IT Revolution, Gene Kim's organization, we've collaborated on several publications about how to do DevOps in an engineering and hardware environment, right? And they're bringing in their knowledge from working at Northrop Grumman and Lockheed Martin, and this most recent round we had somebody from Amazon from their AWS hardware group. So there's several articles that talk about principles and practices and give examples. There's several articles there. The question is, what Agile Hardware Conference? It's not a conference. Well, they do speak at his conference. It's IT Revolutions. The name of the conference is IT Revolutions, and Gene Kim's group. Suzette and Robin are regular speakers there on the industrial DevOps topic.
Okay, then there is a comment of the classic way of hard risk mitigation is sit in the thing until it's deemed ready. And what about investing money in the earlier prototypes? How to convince them that? How do we actually do this transformation from except sitting on the problem into actually doing the rapid iterations?
Yeah, that's a
money on that.
Yeah, that's a great question, and that's hopefully what this workshop is doing. It's giving the examples of the people that are actually doing it. You know, NASA. That my go-to, really, frankly, is that NASA video, and I think it's about 7 or 8 minutes in where Jim Bridenstine talks about the economic benefit they've gotten from SpaceX. Right. So NASA historically, we're going to build this rocket one time, and that launch is going to be perfect. SpaceX's approach is we're going to launch rockets every 3 months. And certainly it's very expensive. It's expensive to do a rocket launch, but they have found ways to burn those costs down, right? We're going to drive the cost of individual launches down to make it more economical. And again, what we don't appreciate is the cost of delay. What is the cost of not launching, and the learning we're going to get from that rocket? Again, that launch, that SN8 launch learned something for SpaceX. And learning that now versus learning it 2 years from now, what's that cost of delay, or even 8 months from now, right? And we don't put that in the equation. And that's Don Reinerson's. You know, I love Don Reinerson and the way he drives things economically, right? You can't say that it's more expensive to do it this way until we can quantify the cost of delay of not doing it now. And certainly this is the way those hardware companies are developing and innovating and iterating.
There's actually still a lot of good questions. We are hitting 4 o'clock deadline. We should close this conference. Maybe one more. There's a question about functional safety to this approach.
Oh, I just saw one pop up. Could functional safety development follow agile approach? Currently, we are using the V model. So we talk about compliance and safety, the notion of building the quality in. So we want our compliance built in. I'd recommend for guidance there. Although it's a little old, I think it's still very relevant. If you go to Scaled Agile Framework and Nexus Solution Intent, there's an article on compliance. It talks about how we want compliance to be built in. Every launch that SpaceX has, SpaceX is probably a little different. My go-to here is talking about Waymo, Google's autonomous car division. I happen to live in the Phoenix area, the Chandler area, where Google has been testing all of its cars. If you go to Chandler, Arizona, and sit on a corner, this is kind of pre-COVID, there's less of them now once COVID hit. But if you sat on a corner in Chandler, Arizona, in a 10-minute period, you would see no less than 4 or 5 Waymo cars go by. They were everywhere. They were like ants, right? And I'd ask people, how often do you think they update the software in those cars? It's probably every day, right? And how often do they update the hardware in those cars, right? It's probably less than every year, maybe even less than every month, right? Every time there's a new board or a new something, they're updating the hardware as well. Does that car still need to meet our National Transportation Safety Board and Automotive 26262 compliance? And if that car got in an accident, would somebody want to sue them and be able to? And the Waymo cars have gotten in accidents. So all the functional safety that we expect in our autonomous vehicle, our vehicles, also have to apply to those Waymo vehicles as well. And how do they do it? They do it by building the quality in. They don't have separate phase gate reviews and separate functional safety people and attending separate meetings. They're building that quality in, and they're building it in with automation. And the way we describe that and how we call that out in SAFE is described in that compliance article. Or if you have any further questions, just you can reach out to me or Mart at harry@scaledagile.com.
So there is also this book from Paolo Samieli, which is called Extreme Manufacturing. And one of the things about the safety test is that you can actually design against the safety test and simulate for example, crash collision tests before you actually start building the hardware. And that saves some money and saves some time. So that's also an interesting approach, that you have this kind of borrow this test first approach from software practices and apply it in the hardware to avoid some cost and increase the speed.
Yeah, and that individual, he also, I think, is part of the WikiSpeed group we mentioned, Joe Justice's group, I believe. And what they claim is that their simulations are so accurate that and this is in the U.S. government, that our government allows them to make changes and validate it through simulation instead of having to crash a car, right? For certain types of changes. So they actually can validate through simulation as opposed to being validated through crashing a car. So yeah,
so we are a little bit over time here. So you can also reach Harry at harry@scaledagile.com and me at Maarit Laanti, MAARITLAANTI@nitor.com and itor.com. So happy to have you over here and have a good day.
Yeah, thanks everyone. Thanks for attending.
Yeah, thank you. Bye-bye.